fraction of order of 10 to the minus 4. And then when the first stars form, the photon they emit re-ionize the universe. So around a redshift of 7 and re-ionization, this fraction goes up again. The ionization fraction is crucial in order to understand the evolution of the Thomson scattering rate, here per unit of conformal time, given by the Thomson scattering cross-section, times the number of free electrons, which you can decompose as a total number density of electron, times the ionization fraction. And the scale factor is here just because we are defining our scattering rate with respect to conformal time. So sigma t is a constant, and so when the ionization fraction is a constant, which is true in the early and late universe and in the middle, the scattering rate scales like 8 to the minus 2. So you have here some region where the scattering rate goes down like 8 to the minus 2. And then when xe goes down or goes up exponentially, you have this exponential drop or this exponential rise here. And what is really interesting is to compare the scattering rate with the Hubble rate. You know that the condition for the mechanism to be efficient in the universe is that the interaction rate should be larger than the Hubble rate. The Hubble rate goes down, but more slowly than the scattering rate. And importantly, the two cross each other just after recombination. And so that should be the time when the universe becomes transparent, because it's a time when Thomson scattering ceases to be efficient. And the photons have a mean free path that goes very quickly from 0 to infinity. And so finally, they can bring an image of something remote, and we say that the universe becomes transparent. It's also fun to note that at reionization, in principle, because the ionization fraction goes up, the photons in the universe could recombine. And if this was the case, the universe would become opaque again for a while, and we would be unable today to see the CMB last scattering surface from recombination. We would only see a kind of last scattering surface from reionization. Fortunately, this does not happen, because when Xe goes back to 1, there has been a dilution with this factor 8 to the minus 2, such that the interaction rate does not reach anymore the Hubble rate. And the fact that the blue curve fails to go above the red curve means that reionization will be a small effect. The photons do not recombine. We can still see what happens at recombination, but with some blurring caused by reionization. Once you have found this interaction rate, you can integrate it along the line of sight in order to find the optical depth, which is the thickness of the cosmological fog. You do the integral from some arbitrary time until today. So by definition, this optical depth is equal to 0 today. And here I put it in log scale. So today it goes back to minus infinity in log scale. But then when we go back in time, this curve goes up because you integrate the area below the blue curve here. And you see that if you choose an earlier time, which is between now and recombination, the earlier time you choose, the more area you have below the curve, so the optical depth goes up. But then when you choose an early time eta, which is before reionization, your integral is not going to change because you are adding to the surface below this area some negligible surface from this area. And so you reach a plateau which quantifies the thickness of the fog created by reionization that will blur the CMB. And so the parameter which is relevant here is the integral below the blue curve, which is called the optical depth to reionization. It is this plateau. And then ultimately, when you choose an initial time around recombination or even before, again, you catch up very large contributions to the integral, and the curve goes up to infinity. And when t exceeds 1, then it means that the fog is very thick. You cannot see behind these points. And this is a region where the universe is opaque. Finally, after defining the optical depth, you can go to the next step and define a function that will play a huge role in our mathematical description of the CMB. And this is the visibility function. The visibility function is minus tau prime exponential minus tau. And with a small exercise of probabilities, you can show that this is a distribution of probability normalized to 1, and it gives you the probability that the photon from the CMB had its last scattering that we observed today, had its last scattering at eta. So gamma just gives you the probability interaction of photons at a given eta, but gamma is not the probability that a photon had its last interaction at eta, because the photon could interact at an early eta and re-interact later. And so you need to penalize gamma by a factor smaller than 1 if you want to obtain this visibility function. Minus tau prime is nothing but gamma. And this gamma here is multiplied by a factor smaller than 1, which suppresses the probability, which accounts for the fact that the photon should not have rescattered later on. And so the combination of these two factors gives you this probability function. And I plot it here. All the plots are done using some class notebooks. Most of them are public, and you download them when you download class. So this is conformal time. This is a visibility function. And the visibility function has two peaks. But the second peak is, so the first peak is very high and narrow. The second one is very low and wide. And here, in order for you to see the second peak, I multiply the visibility function by 2 orders of magnitude only in this range. Now, when you integrate the area below this curve, you find that 94% of the area is below the recombination peak and 6% below the reionization peak. It means that today, when we detect the CMB photon, there is a 94% chance that it last interacted at recombination, and thus it brings us a nice image of the CMB last scattering surface. And there is a 6% chance that it last interacted during reionization, and then the role of these photons will be to blur the nice image from the primordial CMB. Okay, I'm nearly done with this part on the thermal history of the universe, at least the aspects relevant for the CMB. The last quantity I want to introduce is the diffusion length. The diffusion length will play a very big role later on. So in the early universe, where Thomson scattering is very efficient, the photons have a negligible mean free path. And then at the approach of recombination, because Thomson scattering becomes gradually inefficient, the mean free path will gradually increase. And with all the rescattering of the photons over electrons, we will have some kind of Brownian motion of photons with a growing mean free path. And at some point, the photon has its last interaction and starts to propagate in straight line indefinitely, or maybe until it reaches the detector of a human CMB experiment or something like this. So the mean free path is given by the speed of light divided by the interaction rate, and this is a quantity that goes from 0 to infinity. And because of all this rescattering, what is interesting to measure or to quantify is a distance traveled by a photon between its initial position and a later time eta. And for this, you have to, so if the photon was always going in straight line, you will need to integrate over the mean free path, C over gamma. But because the photon is always rescattered, you do like a random walk, and in order to get a good approximation, instead of integrating over the mean free passes, you integrate over the square of the mean free passes, and then you take the square root, like in a Pythagorean version of the integral. So this is done by building this integral where you multiply the mean free path by the interaction rate. You integrate, you take the square root, and you get this diffusion length. That will be important later on. Next step. We are going to talk now about linear cosmological perturbations. So most of you already had an introduction to this topic. I will go a bit fast, but I restart from the beginning. So we describe the geometry of the universe with a metric field with conformal time and position. And we describe different types of matter with their stress energy tensor, which we decompose each of them into background quantities and perturbations. And we are a bit stuck when we realize that each of these perturbed tensors have 10 degrees of freedom, symmetric 4 by 4 tensor. So that's a lot. It could compromise the mathematical description of fluctuations. A lot of order was brought by this great paper from James Bardeen in 1986, where Bardeen had this intuition that we define perturbation in a very special background. It's a background which is assumed to be homogeneous and isotropic. That's a Freeman-Lemaitre assumption. And thus the background is invariant under spatial rotation, under the group SO3. And because of this, Bardeen has the intuition and is able to prove mathematically that the perturbation can be classified in 3 sectors which decouple at linear order in perturbation theory. The sector of scalar, vector, and tensor perturbation, where the name refers to the way in which these quantities transform, not under Lorentz transformation, but under spatial rotation. So in particular, a vector here means a 3 vector, the usual vector. And Bardeen shows that the 3 sectors account for completely different physical mechanisms. The scalar sector is a generalization of Newton theory. It tells you how an overdensity creates gravitational forces. The vector tensor describes something which is very specific to general relativity called gravitomagnetism. It encodes all the effects of the gravity created by vorticity in matter. And the tensor sector accounts for gravitational waves. So these 10 degrees of freedom are distributed as 4 scalar, 4 vector, and 2 tensor for each perturbed quantity here. And the lecture, we will be able to focus on scalars. So vector degrees of freedom do not play a role in the standard cosmological model because vectors are unstable. They continuously, if you source them, they continuously go to 0. They are driven to 0. So model only in very exotic cosmological model, for instance, with topological defects, would you be interested in vectors? So we forget about vectors. Tensors will play a role in the CMB, but we will see this at the very end. And since at linear order, all these sectors decouple, we really have the possibility to choose one sector and study only this sector independently. And so we will study the scalar sector. This is where most of the relevant CMB physics will take place. And then we have this gauge freedom in general relativity. So I don't have time to spend time on the mathematical description, but the idea is simple. If you have a universe with small perturbation, you want to define your quantities mathematically, you need to choose a coordinate system. You will not choose any coordinate system because you want a coordinate system in which you can use perturbation theory. And so you want to use just the coordinate systems in which on a constant time hypersurface, all quantities appear with very small perturbation. So this prescription eliminates lots of silly choices of coordinates, but you are still, it is still compatible with an infinity of choices of coordinates. And importantly, among the possible coordinates such that on constant time hypersurface you only see small perturbation, among this system of coordinates, there is not a unique time slicing. You can make different choices with different time slicing. And when you change the time slicing, immediately you change the operation of averaging a quantity over a time slice. So your averages will be a bit different. And since the perturbations are defined as a true quantity minus the average, if the gauge choice acts on the average, it also acts on the definition of the perturbation. And so a general coordinate transformation, even if compatible with perturbation theory, might change the mathematical expression of all perturbations. And this is exactly what we call gauge freedom. So what do we do with this? If you would just ignore the problem, you would end up with a bad description where some of your solution of the equation of evolution would be some spurious gauge mode. So you have two choices. Either you work a lot in order to define only gauge invariant combinations of perturbations, and then you find the gauge invariant equation of motion that dictate their evolution. This is very elegant. It adds some work, and it's not necessarily needed, because another thing you can do is fix a gauge. You make a clear choice such that only one coordinate system is compatible with your choice, or at least only one time slicing. And then you stick to this choice. Then you will not have spurious modes. And you could say, yeah, but if I stick to this choice, how do I know that my final prediction will have a universal meaning? Well, it is the case because all the observations we make are independent of mathematical choices. They are physical observations. And so you can prove that if you go all the way to the calculation of an observable, this observable will always be gauge invariant. So even if I choose a gauge and I restrict my calculations to one gauge, if then I go all the way to the calculation of an observable quantity, the result will be gauge invariant. So I don't really need the effort of going to gauge independent variables. So this is a very short summary of gauge dependence in cosmology. And what we will do is fix a gauge. And if you fix a gauge, you can fix two scalar quantities, two scalars, two vectors, but two scalar quantities. And we will take the gauge fixing to our advantage, meaning that we will choose to eliminate 2 degrees of freedom that we find slightly inconvenient. And there are many possible such choices. The one that usually people pick up in lectures, because it is pedagogically more meaningful, it makes things easier to understand, is when you eliminate 4 of the scalar perturbation, 2 of the scalar perturbation of the metric. I remind you that we have 4 scalar perturbations in delta G mu nu. 2 of them have a very, very intuitive meaning. 2 of them have a more complicated meaning. So let's eliminate these other 2. And then we are left with a perturbed metric, which is a background Friedmann metric, plus 2 functions of space and time, phi and psi. Here the metric is written in terms of proper time, and here in terms of conformal time. Conformal time eta is defined such that dt is equal to a d eta. With such a choice, you can factor out the scale factor, meaning that the second metric has a conformal symmetry. And the advantage of this factorization is that it leads to simpler perturbed equation at the end. So usually we will use conformal time rather than proper time. And then we have these 2 functions, phi and psi, whose meaning is really intuitive. This one appears in the G00 term, so it's a local distortion of time. And when you study GR and its connection to Newtonian physics, you learn that the Newtonian gravitational potential is a local distortion of time from the point of view of GR. So psi will play the role of a generalized gravitational potential. Phi appears in a term in factor of the scale factor A. And so you can think that the scale factor A gives you the average expansion rate, and phi gives you a local modulation of this expansion rate. It tells you if in one point of the universe you are a bit ahead or a bit behind the average expansion. So these will be our 2 metric fluctuations. We will see that under some very good approximation later on, we will even be able to assume that phi and psi are equal to each other. And then we focus on matter perturbations. And for matter perturbation, we know that in delta T mu nu of each species, we have 4 scalar degrees of freedom. And we have already used the gauge freedom. So we are not allowed to eliminate additional degrees of freedom. We already use this facility for the metric. So we are going to stick to 4 functions, and we will define them in the following way. We will try as much as possible to use dimensionless function. Delta x will be the relative fluctuation of energy density. So it's a delta rho over the average rho. So it's dimensionless. Theta x will have to do with the bulk velocity of the fluid. The bulk velocity is a 3-vector. It can be expressed as a gradient of a scalar plus a vector perturbation that we don't care about. But if it can be expressed as a gradient of a scalar, it means that it's also completely encoded in its divergence. And so the degree of freedom in which we are interested is not the full bulk velocity field, but only the divergence of this bulk velocity, because it contains all the information about the scalar part. And we will call theta the divergence of the bulk velocity of x. Then we will have the pressure fluctuation in every point, delta px, and we will have something more complicated, sigma x, called the anisotropic stress. And to understand this, imagine that you are looking at a fluid which is not a perfect fluid. If it's not a perfect fluid, there is no reason that an observer in this fluid would measure the same flux of particles coming from all directions, and in other words, would measure the same pressure from all directions. You would be there in the fluid with a shield, and by presenting the shield to different directions, you would get a different pressure. So the pressure could then have a complex structure that you could expand in multiples. And one of these multiples would be special. It would be the quadruple. It would be special because this quadruple of the anisotropic pressure can be shown to be the last scalar degree of freedom in delta T mu nu. And this is what we call sigma. It is a potential giving rise to this quadruple component of the anisotropic pressure. In many fluids, these four functions will not be independent. In many cases, for instance, we will have an equation of state for the fluid. The equation of state holds at the level of perturbed quantity. For instance, if it's a linear one, you will get P equal W rho. You take the average and you get average P equal W average rho. You take the full one minus the average and you get the relation at the level of perturbation, delta P equal W delta rho. So in standard cosmology, we will usually have a relation like this. And it means that we will be able to eliminate delta P as a function of delta rho. And delta rho is in the numerator of delta x. So it means that delta P will not be a free function. It will be possible to infer it from delta x. And then we go from 4 to 3 degrees of freedom per fluid. Additionally, we will often be interested mainly in perfect fluids. In perfect fluids, you have strong interaction. And what do strong interaction do? They isotropize everything. When you have strong interaction in a perfect fluid, everything looks isotropic if you are at rest with respect to the fluid. And in particular, pressure is isotropic, same in all directions, like the usual pressure that we are taught about at high school. And then this sigma vanishes. And then in this case, we only have 2 degrees of freedom to describe our fluid, which are the density, fluctuation, and the divergence of the bulk velocity. Then we are going to describe these fluctuations in Fourier space. Why? Well, it's obviously a good idea because we are doing linear perturbation theory. As long as the equations of motion are linear, if you go from real space to Fourier space, the Laplacian in the equation are replaced by k squares minus k squares, and you end up with a system of equations for Fourier mode which are decoupled from each other. You need a nonlinear equation of motion in order to couple Fourier modes with each other, and this is at the heart of what Misha will describe in this lecture. Since we are doing linear perturbation theory, we know that it's very, very advantageous for us to go to Fourier space because all the Fourier modes will be decoupled. They can be studied independently of each other. But we're in cosmology, and so we do our Fourier expansion, not my Fourier convention here, that's an arbitrary choice. Our Fourier expansion is done with respect to the comoving coordinates x, which makes k a comoving wave vector. So we are used to saying that the wavelength is 2 pi over k. Here, 2 pi over k is only the comoving wavelength. And to get the physical wavelength, we still need to multiply by the scale factor. And so we have this funny situation in which even when I look at a fixed Fourier mode, still its wavelength increases with time due to the expansion of the universe. And what is particularly relevant is to compare the evolution of wavelengths to evolutions of the Hubble radius. The Hubble radius is the speed of light divided by the exponent rate, and it separates two regimes. The super-Hubble regime, where microphysical effects are not important for causality reason, gravity forces, pressure forces are not important. But the structure of the GR equation is very important. In the sub-Hubble regime, then microphysics can causally play a role, like in particular pressure and gravity forces. But then it's GR correction which are unimportant. You can use Newtonian physics. So the Hubble radius is a separation between these two regimes. And we are wondering whether the wavelengths that we observe today in the data were in the sub or super Hubble regime in the past. Today, by definition, if I plot here distances with respect to conformal time, in blue, I show a bunch of observable cosmological fluctuations, or at least their wavelengths. And in red, I show the evolution of the Hubble radius. Today, I know that all my observable wavelengths are sub-Hubble, because otherwise I would not see them, for the simple reason that the Hubble radius today gives you an approximation for the observable radius of the universe. So today they are sub-Hubble, but when you solve the equation, you realize very, very easily that in stages with decelerated expansion, like radiation and matter domination, it's very easy to show that the Hubble radius must grow faster than the wavelengths, which means that when I extrapolate back in the past, my observable wavelengths were super-Hubble. They entered inside the Hubble radius one after each other, starting from the smallest one. And this will play a big, big role in the understanding of linear perturbation theory. The condition for Hubble crossing, so the condition for being at the intersection between the blue and the red line, can be written in different way by just equating lambda and RH. You can show that on this line, the wave number is of the order of AH or 1 over eta. So a nice compact way to write that the mode crosses the Hubble radius is to write k eta is of order 1. And then we need to find equation of motion for our perturbations. And we start from the linearized Einstein equation. There are many of them, and in particular, 4 of them in the scalar sector. We will be mainly interested in the 0-0 equation. The 0-0 equation gives a relation between the density fluctuation and the metric fluctuation, and as such, it should be a generalization of the Poisson equation of Newtonian physics. So on the right-hand side, we have a sum over the delta rho of this species x that I can write in this way. On the left, I have different metric fluctuations. And in particular here, you see that there is a term connected to the Laplacian of phi, like you have a Laplacian of the gravitational potential in the Poisson equation. Then you may also wonder how to recover the usual Poisson equation. And for this, you need to go to the sub-Hubble limit. If you go to the sub-Hubble limit, then we said k should be bigger than AH in the sub-Hubble limit. AH is the same thing as A prime over A, where the prime is a derivative with respect to conformal time. So being sub-Hubble means having k bigger than A prime over A. And then it's obvious that this term dominates over this one. We will find that this one is also negligible because on sub-Hubble scales, variations of the metric fluctuation are never really important. So in the sub-Hubble regime, you only have an equality between this term and the right-hand side. And this gives you the usual Poisson equation with here a physical Laplacian. Minus k squared gives you the comoving Laplacian, minus k squared over A2 is a physical Laplacian. And we see that the Laplacian of the gravitational potential is sourced by the total energy density perturbations, which means that the gradient of phi gives you gravitational forces sourced by overdensities of matter in the universe. If we would be in the opposite limit of the super-Hubble regime, it would be the opposite. The term with A prime over A squared, which is the last one, would dominate. And then our approximate equation would give you an equality between this term and this term with the appropriate factor. And after using the Friedman equation, you would get an A prime over A squared here. You would replace it using the Friedman equation. It would give you a rho total. The rho total would simplify with the rho which is on the right-hand side. And you would end up very, very quickly with the result that 2 psi is minus delta total. So on super Hubble, we have a relation between metric fluctuation and density fluctuation, which has nothing to do with the Poisson equation. It comes from completely different things. It comes really, in this case, from full general relativity. And we will use this when we will try to understand initial fluctuations in the universe. We won't use much the other equation, the other linear Eisenstein equation. Note, however, that from the IJ equation, I can extract a nice combination. And this nice combination will tell me that the difference between the two metric fluctuations is sourced by the total anisotropic stress. So that's interesting. If we had no anisotropic stress in the universe, there would be only one scalar degree of freedom in the perturbed metric. Actually, this will usually be a very good approximation because the universe mainly contains perfect fluids. The imperfect fluid will be neutrinos after their decoupling, but they play a very small role, and photons after their decoupling. But since the decoupling of photons takes place during matter illumination, after their decoupling, photons are not very important anymore. So in most applications, it will be a very good approximation to neglect the total anisotropic stress in the universe and to work under the approximation where phi is equal to psi. And the other equation contained in the linear Eisenstein equation could be written, but they could also be written in the form of Bianchi identity. And this is what we will do, and we will move to the equation of conservation of energy and momentum. And then we can get an equation of conservation of energy and momentum for each decoupled species, or for the total. For the total, that would be the Bianchi identity. For each decoupled species, it's the same, except that I put a little x to show that I'm dealing with a perturbation of a species x. So we have one equation of conservation for energy, called the continuity equation, and one equation of conservation for momentum, which is called the Euler equation. They are very similar to hydrodynamical equations. So they give us a derivative with respect to conformal time of density fluctuation and bulk velocity. And on the right-hand side, we find delta, theta, and metric fluctuations. Oops, we also find anisotropic stress here. That's a problem because it means that when I have anisotropic stress, these two equations do not form a closed system. But that's not the case, at least for cold dark matter. For cold dark matter, we have negligible pressure and stress, so we have a closed system. For electrons and baryons, because they are non-relativistic, they also have negligible pressure, so we can also neglect their anisotropic stress. The difference between the equation of motion for cold dark matter and electrons or baryons is that these two are coupled to photons through Thomson scattering. So the covariant derivative of delta T mu nu for electrons or baryons is not equal to 0, but is equal to the momentum transfer term between electron baryons and photons. And this term will just add up to the Euler equation, not to the continuity equation, because it's a momentum exchange and not an energy exchange in the Thomson scattering limit. And so for electrons or baryons, you should add here a term which contains the Thomson scattering rate that I can express as a gamma or as a tau prime, multiplied by the difference between the velocity of baryons and photons. And we will see what is the role of this term later on. Okay. I can anticipate, I can tell you that the role of this term is that if the baryon and photon velocity are not aligned, so if the parenthesis is not 0, and if tau prime is non-negligible, this term will push on the derivative of delta in a direction such that delta will evolve to make the parenthesis go to 0. This is what happens typically, for instance, also in the Boltzmann equation. So the role of this term is to push the system towards a solution where theta b and theta gamma are equal. It means that Thomson scattering wants to align the bulk velocity of baryons and photons, which is very intuitive since they exchange momentum. Okay, when I have photons and neutrinos, which are decoupled, then there are no strong interaction that can isotropize pressure any longer. So we have an isotropic pressure, we have a non-zero sigma, and this does not form a closed system, which means that in this case, the continuity and Euler equation are not the fundamental equation of motion of the fluid. There is a more fundamental one, which is the full Boltzmann equation. And for the full Boltzmann equation, we go to the level of introducing a phase space distribution for photons or neutrinos. For photons, we could call it F gamma. And then the Boltzmann equation would tell us that the total derivative of F gamma along a geodesic is given by the coupling between the photon and the electron. And for neutrinos, it would be the same, but in a collisionless version. Okay, but so as a conclusion, for cold dark matter and baryon, we will use the equations of this type. And for photons and neutrinos, we will use Boltzmann equations. I didn't mention that there are some mysterious coefficients in this equation. Well, they are not so mysterious. W is the equation of state parameter. I assume the linear equation of states. CS is a sound speed, which is such that the square of CS is a ratio of pressure perturbation over density perturbation in each point, delta P over delta rho. And CA is another quantity with the same dimension. It's the adiabatic sound speed, which is such that the square of CA is given by the time derivative of the homogeneous pressure divided by the time derivative of the homogeneous density. So this is a background quantity. This is in general a perturbation quantity. Okay, so this is the shape of the equation, and we can do a little summary where we have here the functions that describe our universe, the degrees of freedom, and here their equation of motion. So we have two metric fluctuations, the gravitational potential psi and the scale factor distortion phi. We describe cold dark matter with a density fluctuation and a velocity parameter. The same for the baryons. We describe photons with a more complicated Boltzmann phase space distribution, and neutrinos also with a phase space distribution. It's really more complicated because the first function only depends on time and space. The phase space distribution depends on time, space, on the momentum of the particle, and on its direction of propagation that I call n hat. It's a unit vector. And so P and n hat form the three momentum of the particles. So that's because the phase space distribution, of course, is defined in phase space. And now we have a well-matching number of equations of motion, fortunately, because for the metric evolution, we have this Einstein 0,0 equation that we just looked at. And we have the equation telling us that phi minus psi is given by the shear. For cold dark matter, we have a continuity and Euler equation. The same for baryon, with just the additional Thomson scattering term. For photons and neutrinos, we have a more complicated equation that we did not write explicitly. So let's try to be a little bit more specific on this Boltzmann equation, but without going into horrendous mathematical details. We can use the fact that in the early universe, the photons have a black body spectrum, so a Bose-Einstein spectrum with zero chemical potential. For neutrinos, it would be a Fermi-Dirac spectrum, and we just learned that the Fermi phase space distribution was invented here. That's quite remarkable. So for photon, I write my Bose-Einstein distribution because I know that in the early universe, photons were in thermal equilibrium. They had to obey to such an expression where the dependence on momentum is entirely captured by this exponent. That's the difference between this particular expression and a general phase space distribution. And then you could tell me, okay, in the early universe, I buy the fact that photons have a Bose-Einstein distribution, but I'm not sure that this will be preserved by the later evolution. And then you can use a very nice argument. you can try to think how to create departures from this relation once photons are decoupled. Once they are decoupled, each individual photon is in free fall and obeys to a geodesic equation. You can write this geodesic equation in your perturbed universe in the Newtonian gauge, and you can put it in this form. On the right, we have a metric fluctuation. On the left, we have the logarithmic derivative of the product AP with respect to conformal time. And we see already that in a homogeneous universe with no metric fluctuation, this will be equal to 0. It will mean that P scales like 1 over A, and this is a well-known result for the redshifting of photons. But in a perturbed universe, you get correction to this. The first one comes from the derivative of phi. It's a dilation effect. It means that if locally you have more expansion, then locally you will redshift your photons a little bit more. It's a gravitational redshift effect. And this is a gravitational Doppler effect. It's a contraction of the direction of propagation of the photon with a gradient of the gravitational potential. So this term is non-zero when the photons are entering or leaving a gravitational potential well. And you know that because of the gravitational Doppler effect, they will gain or lose energy, and this will show up at the level of their momentum. So these two terms change the momentum. And you could say, since they change the momentum, each individual photons get a different momentum change, and the propagation of the photon in the perturbed universe is going to break down this nice blackbody expression. Well, it's not the case because, and it's very apparent when you put the geodesic equation in this form with a d log p. The d log p is a dp over p. And it shows you that independently of the momentum of the photon, the relative momentum shift, dp over p, is the same for all photons traveling over the same metric fluctuations. So traveling over overdense or underdense region will shift the momentum of a whole flux of photons, but they are all shifted in the same way such that the change can be expressed as a local variation of temperature, but not as a departure from the blackbody spectrum. And that's a very powerful argument. So we have seen that gravitational interactions at linear order are not able to distort the blackbody shape. And it means that we can use this parametrization of F at any time, even after photon decoupling. But if we are after photon decoupling, the temperature here is not anymore a thermodynamical parameter resulting from thermal equilibrium. It's just there because we created the blackbody shape initially, and we don't depart from it. So it just stays as a parameter in the phase space distribution. But now it's interesting to look at the arguments of this parameter. Here I wrote eta, x, and n. Why? If I would be in the early universe, I would have thermal equilibrium in every point. So in every point with coordinate x and time eta, I could define a temperature, and I would have no dependence of t on the direction. But if I am after photon decoupling, I'm no longer in thermal equilibrium. T is just some kind of parametrization of the blackbody shape. And there is no reason for which T would not depend on the direction of propagation. And to see this, imagine that you are an observer in the universe after photon decoupling, and you see photons coming from different directions. There is no reason that these photons come to you with the same parameter T for many reasons. First, they decouple from different regions. Some could be overdense, some could be underdense. Then they traveled over different metric fluctuations and in different directions, meaning that they were modulated by a different effect of the phi prime along the line of sight and of n gradient of psi along the line of sight. So, through propagation, the temperature of the photon, which is no longer a thermodynamical temperature, acquires a dependence on the direction of propagation. This will be very important, and in order to get a nicer mathematical description, we will expand this temperature as a background temperature T bar averaged over all position and direction, and that's a T bar equal 1 over, that scale like 1 over A, and which is equal to the CMB temperature today of 2.7 Kelvin, multiplied by a relative fluctuation theta, big theta. So this will be the temperature anisotropy of the photon. And it's, by definition, it has to be a function of time, space, and direction of observation. So what can we do with this theta? Since it has a dependence on direction, we can expand it in spherical harmonics. We will get a monopole, we will get a dipole, and we will get higher multipole. The monopole is the temperature fluctuation integrated over all direction. And this gives you up to a factor 1/4 the density fluctuation of the photon. And if you want to understand the factor 1/4, remember that for relativistic species like photon, the density fluctuation is in T⁴. So if I differentiate this relation, I get delta rho gamma over rho gamma bar equal 4 delta T over T bar. I call this delta gamma. I call this the monopole of my temperature anisotropy. And I get theta 0 equal 1/4 of delta gamma. And this is only a function of time and position. What about the dipole? The dipole is just telling me that if I am an observer in this universe, I see a bigger flux from one direction, a smaller flux from the other one, and a cosine modulation between the two. This is typically what happens if, as an observer, I'm not in the rest frame of the photon, and thus I measure a Doppler effect. So this dipole term is in fact just given by the peculiar velocity of the photon with respect to the coordinate frame. If the photons have 0 velocity in the coordinate frame, there is no dipole. The higher multipole can appear because our photons have decoupled. So for the reason that we mentioned before, each photon has its own history and can develop its own temperature. And so in general, you would expect to see a very complicated structure of higher multiples if you would be an observer. Now, we take the Boltzmann equation, we linearize it at order 1 in perturbation, and we replace the variable f gamma by this theta in order to get a more intuitive form. So after pages and pages of nasty calculations, you get this very simple equation. Well, it doesn't look maybe so simple at first sight, but in fact, you will see that it has a very intuitive meaning. So it's a first order differential equation for theta with different terms. If you had only the first two terms, and this equal to 0, it would be a usual diffusion equation saying that overdensity propagates like plane waves in the universe. Just this, free propagation. We don't have free propagation. We have two terms related to the metric and a term related to Thomson scattering. The terms related to the metric are the same as in the geodesic equation before. It's not a surprise. They account for the same effect in the geodesic equation written for a single photon and here for a flux of photons. So when you have dilation effect or gravitational Doppler effect, all the photons get blue shifted or red shifted, and this can be expressed as a shift in their temperature. So it acts directly on theta. And then if Thomson scattering is non-negligible, we have this very interesting term, which has a Thomson scattering in factor, like in the structure of any Boltzmann equation. And then what you find is a parenthesis where you have the difference between the velocity of photon and baryons projected along the direction of propagation, plus higher multiples. So you know how Boltzmann equations work. They tell you that when you have a very efficient coupling, when gamma, the term here is extremely large, then any departure from parenthesis equal to 0 will have a very, very quick effect. Theta prime will be non-zero and will readjust to a value where the parenthesis goes to 0. That's how a Boltzmann equation always works. And in our case, we see that if the Thomson scattering rate is large, gamma will evolve in such a way that the two velocities will become equal to each other. That's what we said before. The baryon and photon velocity will align on each other, and all higher multiples will vanish, which is extremely intuitive because when you have strong interaction in a fluid, what happens? Isotropization. Interactions want isotropization. And once you have isotropized your fluid, you have no more temperature anisotropies, at least if you are in the rest frame of the baryons and the electrons, which is a rest frame in which Thomson scattering occurs. So that's exactly what this parenthesis means. It means that Thomson scattering wants to align the velocity of photons and electron baryons and to wash out higher multiples. So nice, we understand this equation now, and still it's not very practical because theta is a function of time space. We are used to it. When we have functions of time and space, we do Fourier expansion, we know how to deal with it. But we have direction of propagation here. So this is a function with a quite complicated mathematical structure. And to make it more tractable, we are going to do transformation. First, a Fourier transformation, such that the dependence on x will be replaced by a dependence on the co-moving Fourier mode. But then we will do a Legendre expansion. The Legendre expansion is a particular case of a spherical harmonic expansion for functions that depend only on one angle and not two angles. And in this case, instead of spherical harmonics, you have the Legendre polynomial of the cosine between these two angles. So you could say, wait a minute, why are you doing a Legendre expansion and not a spherical harmonic expansion? Well, you can prove that when you deal with scalar perturbation, and the Boltzmann equation has this form. The gradients always appear combined with the direction of propagation. In Fourier space, this will give you the cosine of the angle between the direction of propagation and the Fourier mode. And so in your equation, at the end, you only get one angle. And there is no other way in which another angular dependence could appear. It will not be true for tensor, but it's true for scalar perturbations. So you can simplify things a bit. Instead of the full spherical harmonic expansion, you can do this Legendre expansion with a Legendre polynomial, and you obtain a set of multiples theta L and not theta Lm, like in a general transformation. So L is a multiple number, and then you plug in this Legendre expansion in your full Boltzmann equation, which was written here. You identify the terms multiple by multiple, and you obtain this famous hierarchy of equations. This is the equation for the monopole, for the dipole, and for higher multiples. And unsurprisingly, because stress energy conservation must still be fulfilled by photons, the first equation for L equals 0 is nothing but the continuity equation of the photons, similar to the continuity equation we wrote before. And the L equal 1 equation is actually the Euler equation of the photon. But the new thing is that we have other terms, and if we would in principle integrate up to L goes to infinity, we would have a closed system of equations. Before we had the problem that we didn't know what to do with sigma. Sigma relates to theta 2, the quadrupole, and now we get an evolution equation for theta 2. Note that every L couples with its nearest neighbors. So if I want to solve for theta 2, I need to know the evolution of theta 3, but this is given by the next level. So I have this infinite hierarchy of equation. And this is what Einstein-Boltzmann solvers, like the historical CMB fast or later common class, trying to solve. They don't go to L equal infinity, but they use some nice truncation scheme. We will come back to this later. So we have our equation of motion for photons. For neutrinos, it would be the same without the Thomson scattering. So we still have 10 minutes, but okay, I will go back here and breathe a little bit. So we have described our degrees of freedom. We have described our equation of motion. Now we have seen that the Boltzmann equation for photons and neutrinos can be rewritten in terms of this hierarchy of equations. And having understood this, we will go to another topic, which is why are cosmological perturbations stochastic? But let's rest a little bit and let me ask if you have any question up to this point. If not, I will slowly continue on the next section. All right, so now we will summarize what it means that the theory of cosmological perturbation is a stochastic theory. This is really important. And in particular, if you don't understand this perfectly at the linear level, you will quickly get lost by the nonlinear perturbation theory. Okay. Taking the point of view that inflation is the right mechanism giving rise to perturbation in the early universe, then it's obvious that it's a stochastic perturbation theory because all the fluctuations that we see have been created by quantum fluctuations during inflation, which are random fluctuations. And especially if we have canonical single field inflation in the early universe, then there are some things which are pretty clear. If you go beyond this scheme, it will be a bit more complicated, but we wouldn't know how to handle it anyway. So in canonical single field inflation, when you quantize the perturbation of the inflaton field, you very quickly see that all fluctuations are stochastic, coming from the randomness of quantum mechanics, and that the evolution of Fourier modes are independent, coming from the linearity of the equations of motion. And it's a very good approximation to use linear perturbation theory in the early universe, because the early universe is when all fluctuations are extremely small. But more than this, inflation guarantees that, or at least canonical inflation guarantees that each Fourier mode has Gaussian statistics. And this simply comes from what you learned on harmonic oscillators. Quantum harmonic oscillator have a wave function which has a Gaussian expression. And here I'm not talking about the wave function, but about the probability distribution of the amplitude of the fluctuations. And you can show that this has to do with the square modulus of the phase space of the wave function, which is precisely a Gaussian if you assume that your quantum modes are initially in the fundamental state. So this comes really from the properties of the quantum harmonic oscillator. Each Fourier mode is then described as a quantum harmonic oscillator in an expanding universe. So if each mode have a Gaussian statistics, then we know that they are entirely described by their variance for each wave number. And the variance for each wave number is what we call Orlov structure. And then for each Fourier mode, we can prove, and this is a really important part, that all the perturbed degree of freedom are related to each other in the sense that they are fully correlated on super Hubble scales. And that's the idea of adiabatic initial conditions. What happens is that all the perturbations in the early universe are created by the fluctuation of a single degree of freedom, which is the inflaton perturbation. And for this reason, all the fluctuations are fully correlated. Where I had an excess of inflaton perturbation, I know that I will have an excess of all other quantities, and vice versa for underdensities. And so you can obtain some very famous and nice relation between all the perturbation of the degrees of freedom. And if you want to show them, it's easier than you would think. You just need to say that for any quantity A, it could be a delta, it could be a theta, it could be a metric fluctuation. In a model of the universe described with canonical single field inflation, then the general perturbation, which should be a function of time and space, is given by the modulation of the background quantities A bar, which are only a function of time, but modulated by a time-shifting function. That's a very powerful argument. Of course, this would not be the case in any universe, but we believe that it's the case in our universe. First, because we had some theoretical prejudice about this, and then because these theoretical prejudice have been confirmed by observations, in particular from Planck. So why is this the case? So all fluctuations come from one time-shifting function, because in the early universe, all fluctuation emerge from the fluctuation of a single degree of freedom, the inflaton field, which plays the role of a single clock, which is the only reason for which you have perturbations. So you can see delta n, eta, as a reformulation of the perturbation of the inflaton. And even if you had more than one inflaton, but if later all species were in thermal equilibrium, then it is the temperature that would play the role of delta eta. All the fluctuation would be related to the fluctuation of temperature. So you have even a redundant justification for taking this relation. Once you take this relation, you Taylor expand A bar into a background and a perturbation term. You do this for each density perturbation, metric fluctuation, and then it's a trivial exercise to show that you have this kind of relation between the deltas. So delta gamma equal to delta nu equal 4/3 delta B equal 4/3 delta C. The 4/3 come from the fact that photons and neutrinos are ultra-relativistic, baryon and cold dark matter are not. So if I would use this argument for baryons, I would have rho baryons proportional to T to the 3. And by differentiating, I would have delta rho B over rho B bar equals 3 delta T over T. But this delta T over T is the same as here. And so I get the equality between the deltas up to the factor 4/3. So this is very easy to understand using just thermal equilibrium. But you can show it also from this general relation. And moreover, when you plug this inside the Einstein equation, you get that on super-Hubble scales, and we define initial condition only on super-Hubble scales, these deltas are related to the metric fluctuation. We have seen already before that on super-Hubble scale, we had minus 2 psi equal delta tot. And here I write the initial condition during radiation domination when delta tot is equal to delta gamma and is equal to delta nu. And finally, if I solve the 0-0 Einstein equation, which is a differential equation with respect to time, I find that all these modes are constant, and I say that in the Newtonian gauge, all fluctuations appear as frozen on super-Hubble scales. So all this comes from this assumption, which is very well physically motivated. Some people say that adiabatic initial conditions are contained in these equalities. For me, these equalities are more a consequence, and the fundamental idea behind adiabatic initial condition is this equality. Okay, what does this imply? It will imply a simplification for our Prandtl power spectrum and all other power spectra. So, we have already seen that canonical single field inflation guarantees stochastic perturbation, which have a Gaussian statistics. We have seen that for each Fourier mode, all degrees of freedom are related to each other on super-Hubble scales. And so this means that I can express my initial conditions by referring to a single reference function. Since I have this relation, I could relate all my initial conditions to just the knowledge of the variance of delta gamma, and I would know all the other variances. But I could choose as a reference the variance of delta B, or the variance of phi, or of psi. So I have different choices in order to express or normalize my initial condition. It's completely arbitrary. So what do? People say that the best would be to express all our initial condition with respect to a perturbed degree of freedom, which is extra nice in the sense that it's completely frozen at all time in the super-Hubble regime. And that's not the case of this function. These functions are constant during radiation domination. They're also constant during matter domination. But at the transition between radiation and matter domination, they have a small jump, like phi m psi, that jump by 10%. It's an effect of the fact that the total equation of state of the universe changes at this transition time. Can we build a combination of our fluctuation, which is truly independent of time in the super-Hubble regime, even at the transition between radiation and matter domination? Yes, and this is the case for what people call the curvature perturbation, because in some gauge, it is the perturbation of the Ricci tensor, of the spatial curvature, And this curvature perturbation is a combination of metric fluctuation and velocity fluctuation. For instance, in the Newtonian gauge, you have this expression. So curvature perturbation will be our reference. It is related to the other perturbations by another factor of order 1. it will be our reference. And we will say that if in one point I know R, then I know all other quantities using this equality. And thus, if I know the variance of R, then I will be able to get trivially the variance of all other quantities. So this is the idea behind choosing the curvature perturbation as a reference for primordial fluctuation. And then the quantity of interest, which a study of an inflationary model could predict, is the variance of R that I express as a primordial spectrum. The primordial spectrum is a correlation between two Fourier modes of R. There is a star because Fourier modes are always complex, even when the real function is real. The function in real space is real. And the primordial spectrum here shows me that when K and K prime are different, there is no correlation. That's what we expected from the fact that Fourier modes are independent. But if K and K prime are equal, then the variance is encoded in a function of only the wave number, which is a primordial spectrum. You could have expected this variance to depend on the vector K, but we live in an statistically isotropic universe. So the variance can depend on the wavelength, but not on the direction. So it's a function of only the wave number K. And the Dirac delta function appears here because I'm referring to an expansion into continuous Fourier modes. If I would define my Fourier transform in a box, then we would have discrete values of K, and instead of the Dirac delta function, we would have a Kronecker symbol of the indices of the K vectors. So this defines our primordial power spectrum, from which all other spectra will be inferred. And moreover, inflation tells us, and then there's a statement I will stop. Inflation tells us that this primordial spectrum is nearly scale invariant. That has to do with the fact that during inflation, all quantities evolve very slowly. So you have an almost time translational invariance that results in all fluctuations acquiring more or less the same properties. If the properties of different scales would be exactly the same, we would have an exactly scale invariant universe. Like in a fractal image, the properties will not depend on which scale you zoom in. And if the power spectrum would be exactly scale invariant, you could show that this P of K should be in K to the power, given the definition I use of the power spectrum here, this P should be in K to the power -3. That would be the exact scale invariant case. Inflation tells me that during inflation, there is a slow evolution of quantities. So I should expect that scale invariance is a bit broken, but it's broken in the form of a power law with a scalar tilt ns close to 1. You can see that if ns would be 1 here, this parenthesis would go away and I would have P proportional to K to the -3. So for canonical inflation, we can use an ansatz for our primordial spectrum of this form with a scalar tilt and an amplitude coefficient here. And this is a good point for ending the first lecture. In the next lecture, we will continue with the definition of initial conditions. We will define the notion of transfer function, and then we will learn how these transfer functions evolve, how to quantify their evolution, and then we will be really deep into the discussion of CMB physics. Thank you very much.
Do you have questions? Yeah. Don't be shy. One question, sorry.
Yeah.
Can you tell in the dynamic expansion function that there are no sigma relates with the fusion?
Yes, I did not show the proof at all. When you expand this in, oh, sorry. Oh, where was I? Sorry, I lost it. It was later here. Okay. Yes. Yes. So if you do this Legendre expansion, the coefficient of θ2 will be P2. And so P2 has the structure of a quadrupole. And before, what I told you is that the anisotropic stress sigma is a component of anisotropic pressure that has the structure of a quadrupole. So you can identify the two. This is really sigma or theta2 are the quadrupole pattern in the distribution of flux of photons around you as a function of direction. So it's not a surprise that sigma is related to theta2 and theta3.
I have a question. Can you comment on what you mean by nearly scale-free in the last slide? Is that
Yes. Well, in fact, if you study inflation in great details, the only thing it shows you is that the power spectrum is not exactly scale invariant, so it can take an arbitrary form as long as you remain close to k to the minus 3. But then there are different expansion schemes to study inflation, and a very relevant one is a slow roll expansion. And you can study inflation at various order in slow roll parameter, which quantifies the scale dependence. And at leading order, you find that the deviation from scale invariance, which would be just 2 pi square AS over K3, can be captured by a power law. And at the next order in the slow roll expansion, you would start to look at the dependence of the scalar index over scale, and so on and so forth. So at leading order, you get a power law, and then in log-log space, you start to see some curvature. This is called the tilt, the running of the tilt, and then you have the running of the tilt, etc. So this is a first order approximation when you keep the leading deviations from scale invariance, which means that in the dynamics of inflation, you keep the first order term in the dependence of all functions over time. Yeah.
mentioned that regarding the composition in identity vector?
Yeah.
But what kind of models, like, not identity?
Yes. So if you have some complicated nonlinear mechanism at some point in the universe, we usually excite vector perturbations, like a phase transition in the early universe with bubble collisions and all this will create vector vectors. But then they will go down, their amplitude will be washed out by the expansion, it will go down like 1 over A. And so very soon, a few e-folds after this mechanism happens, you can already neglect your vector modes. Vector mode would play a role in the CMB if you have a mechanism that are continuously sourcing them. And that's the case when you have a complicated motion of topological defects in your universe. This is really something you need simulation to describe. And then you realize that the motion of the topological defect is a continuous source of all kinds of modes, scalar vectors and tensors. And so when you compute your CMB spectrum in these models, you have a vector contribution. Okay, we have tried to detect this with Planck in particular. We have tried to detect what people call active seeds, which are this kind of continuous sourcing of all modes, and all tests give null results. So it seems that we can really describe our universe with only the fluctuations from inflation, even single field inflation. And then there is really no need to care about vector modes. Maybe sometime a super accurate CMB experiment would see some special shape in the spectrum that would be a signature of vector mode. But if it has not been the case until now, I really think it will never happen because we have already a complete view of the temperature spectrum, very good view of the polarization spectrum, and vector modes seem to be really negligible. Yeah, the constraints are model dependent. It's not, you cannot see a section in a paper saying constraint on vector modes. What you find are constraints on different types of topological defect, constraints on domain walls, on cosmic strings, etc. And In particular, there has been a search for cosmic string in WMAP and Planck data, and there you can see some upper bounds. And then you can translate them into the amplitude of vectors at the time of CMB decoupling. Yeah.
Just a quick question going back to the discussion about the gauges. If my understanding is correct, the density perturbation is like a quantity that's gauge dependent.
Yeah.
So I assume that also means that the power spectrum is also gauge dependent.
Absolutely.
So then if you like fit a power spectrum to CMB or to like a distribution of galaxies, is there like a gauge that you're implicitly using?
Very good, very good. No, there is not, because I told you that all the quantities that you compute at the end, if they are really physically observable quantities, should be gauge invariant. Okay, maybe this is wishful thinking. You need to prove it in every case. And it's very clear in the case of the CMB. In the expansion of theta, all terms excepted theta 0 and theta 1 are gauge independent. And what you measure is a power spectrum for L bigger or equal to 2. So this power spectrum is completely gauge independent. The fact that the first two terms are gauge dependent is obvious. It's related to the fact that if I change the frame, I will see my CMB with a different Doppler effect and a slightly different local value of temperature. So that's trivial and uninteresting. The rest of the CL for L bigger than 2 is completely gauge independent, as it should, because it's an observable quantity.
And then if you did it for like a distribution of galaxies with like redshifts and
yeah, so that's also extremely interesting. For a distribution of galaxies, you have, okay, we say that the matter power spectrum is what we can observe, PM of K. It's a slight oversimplification. Some people have looked at the detail of what you can really observe. And it's a bit more complicated than the matter power spectrum, P of K equal delta square. You have beautiful papers on this by the Geneva group and by also by Lewis, Chanin, Oreta, also by the Zurich group. However, you can usually neglect this small complication, because you find that what is strongly gauge dependent is the result for the matter power spectrum on super-Hubble scales that you don't observe. On the sub-Hubble scale, the gauge dependence is totally negligible. But if you want to solve this problem in an academic way, you can do it by showing that what you measure is a number density of compact object in a given volume in the GR sense, and you do all the calculation, and you can get a gauge invariant version of what you observe.
More questions? Julien, I want to ask you, when you define the temperature perturbations, you had an argument why it did not depend on the on the magnitude of the photon momentum. Go back.
Okay, yeah, I didn't get your question, but you will. Is this the right one? Yeah.
Yes, this one.
Yes.
So theta does not depend on P.
Okay, so
Is this
I think I know what you have in mind.
Yes. So,
it's not a true question. It wants me to say something.
no, because
Okay.
I have an answer, but maybe there are more answers.
So here I cheated you because I'm working at leading order. I told you in the early universe you get an exact Bose-Einstein shape, and then photons decouple, they free fall, so their evolution is given by this equation, and you cannot get any distortion from this shape, so it's still a perfect black body. Now, why did I cheat you? I cheated you because decoupling is a progressive process. So the mean free path of the photon goes gradually from 0 to very large values. Imagine you are a bit before recombination. The mean free path of the photon is small but finite. Then this argument holds, showing that between two interactions, when the photon is in free fall between two interactions, it cannot acquire non-thermal distortions, deviations from a black body. But then when it reinteracts, in principle, it could. I did not give an argument for which it could not. So you can have very small departure from this black body shape imprinted on photons during their last interaction. Not too early, because they were too early, they were in perfect equilibrium. Not too late, because too late, they only feel gravitational interaction, which respect the black body shape. So this effect of the last interaction that can give a bit of momentum or extract a bit of momentum from the photon is responsible for a very small effect, which are the CMB spectral distortions, which are described at the end of my notes, but I don't think we will get there. And you can neglect it in a CMB lecture because it's very small. So you can do everything assuming a perfect black body shape, and then you refine your description taking into account spectral distortions. Essentially, you can say that anisotropies, which are the dependence on direction, are very small compared to the background. Spectral distortion, which are a non-trivial dependence on P, are very small compared to the black body shape. And looking at the two effects together, so anisotropies in the distortion is another two effect, which is probably not detectable. So this is why we can separate these two problems of studying the anisotropies under a perfect black body assumption. And later on, we study the spectral distortion in a homogeneous universe. And both give you interesting information. The information on the anisotropies has been exploited by Planck, WMAP, etc. The information in the spectral distortion, which again is very small, has not been exploited yet because we did not reach the sensitivity to detect these spectral distortions, but it's a very interesting topic for the future. Maybe your question was completely different.
No, I go. No, because I guess I agree.
Yeah.
But the tensor structure are small because Thomson scattering doesn't change momentum very much.
Yeah, you need to go beyond Thomson scattering. You need to look at processes like Bremsstrahlung, inverse Thomson scattering, subdominant processes.
Have some dark radiation that's very strongly. Is it possible that you change momentum enough?
Yeah, of course.
Even leading or
Of course. And then you know that you cannot change it too much. You have the Kobe-Firas bounds on the black body shape, but this can be a way to constrain, and people have done it, to constrain non-standard interaction. So there you have paper by Schluba, by Ali Aimoud on limits on interaction between photons and neutrinos or dark radiation from spectral distortions. Yeah.
Yeah, because I'm not sure I got it right. So you're telling that the moment you would allow for eta towards dependent on P, then you should also allow like for the Fermi distribution not to be a Fermi distribution, but to see the
Yes.
The same order effect.
When you look at very subtle effects taking place in the last scatterings of the photons before recombination, you can add a more complicated dependence of F on P. That's exactly what I'm saying.
Okay.
And then usually it's not a random shape. It's called white distortion, new distortion. It has been studied. So they are like parametric families of deviation from a black body shape.
Okay, so no more left understanding.